Hello and welcome to Lecture 9 for the graduate course ECE 254B, Parallel Processing. This is the last lecture from part 2 prime of the textbook, basically finishing that part before moving to part 3. So this lecture consists of chapters 8B and 8C, receiving roughly equal treatment. Chapter 8B has a lot of material, diverse material. Chapter 8C it focuses on one particular computation, the discrete Fourier transform, which is very important in many applications. Uh, I de-emphasize Chapter 8B somewhat, because this is the subject of the graduate course ECE 252B, Computer Arithmetic, that I teach in spring. And therefore, if you're interested in the ideas in this chapter, you get a lot more of it in that course, 252B in spring, which you can take. So chapter 8B deals with arithmetic and counting circuits. So examples of the circuit model of parallel computation dealing with arithmetic computations. So basically, Chapter 8B focuses on building block computations such as addition, multiplication, division, and counting. Chapter 8C basically takes a more complicated computation, the Fourier transform, discrete Fourier transform. We can envisage a lot of other composite computation and aim to design circuits to facilitate or speed up their execution. Examples include digital filters, encoding circuits, decoding circuits for error detecting and correcting codes. So each of these constitutes a special purpose application. But of these special applications, discrete Fourier transform occupies a very special place and is very important. That's why I devote a chapter to that particular computation. Okay, let's proceed. Uh, this slide I'm going to skip. It deals with bit serial adders at the top and ripple carry adders at the bottom, with which you're already familiar. So let's start with counters. Now, of course, a counter can be implemented by using an adder. So if you want to, say, have a register that contains a count, and then on every receiving every increment signal, assertion of this increment signal, you want to add one. Well, adding one is a special case of addition. So you can use an adder and a register to implement this. However, addition is a fundamentally more complex operation than counting, in the sense that to add k-bit numbers, even if one of them is the special case 1, in the worst case generates carries across the word, the k-bit word, from bit 0 to bit k minus 1, and therefore it takes logarithmic time to execute at best. So here in this slide, I'm presenting a counter design that no matter how wide the register is, it takes constant time. So for 64 bits, 128 bits, 1000 bits, no matter how wide the counter is, it needs a constant time to do the increment operation. So let's see how this works. The idea is to divide the register, the long register that holds the count, into segments, beginning with a very short segment, maybe 2-3 bits at the least significant end, then more bits, then more bits. So each the length of each segment grows as we go from right to left. In this case, I've shown only 3 segments, but this can be generalized to more segments. The idea is to have the counter operate at the speed of this short segment, even though the count is much, much wider, okay? So if I can manage to do that so that every time I increment this, let's say incrementing this 2-3 bit segment takes, let's say, 1 nanosecond. Then I can increment this counter at the rate of once every nanosecond, even though the counter is much wider, and if I used addition, I would need a lot more time. So let's see how this works. So this part is obvious. Every time I assert the increment signal, this is incremented. Okay? Now, this part needs to be incremented after a few cycles of this one being incremented. Imagine this one starting, let's say it's 3 bits wide, okay? Starting with 0, 0, 0, it goes to 0, 0, 1, then 0, 1, 0. Eventually, it gets to 1, 1, 1, 7. And then the next increment, that 1, 1, 1 changes to 0, 0, 0. And the control unit detects this because when this happens, when the 7 goes back to 0, that's the time when you need to increment this one. So this control unit detects that state. And however, instead of incrementing this one, which would take more time given that it's wider, I pre-compute the incremented value during the time when this one is doing its job, during these, let's say, 8 clock cycle, where this one is being incremented and it doesn't generate a signal to increment this part. So the old content plus 1 is pre-computed and it's ready so that when this control unit signals, we just load that pre-computed value into this register. Similarly, if this register, let's say it's 8 bits, this part of the register is 8 bits, then it takes 256 incrementation of this part before this part needs to be incremented. Again, we detect that situation when incrementing this one leads to the need for incrementing this one. Again, this one, which is a very long word, is already incremented, and the incremented value is here available, and we just load it in. Now, because this part has a lot of time to compute that incremented value, because it has to wait for 256 incrementation of this 8-bit part, each of which is 8 incrementation of this. So that's a lot of time. So this incrementer here does not even have to be a fast incrementer. It can be a very simple, low-cost incrementer. Okay? So the idea is that to pre-compute the incremented values for these successively wider segments of the count register, and then whenever the need arises to do the actual incrementation in the register, to simply load that pre-computed value into the register. So using this strategy, I can build an arbitrarily wide counter whose cycle time, the rate at which it can count, is dictated only by this short counter of 2-3 bits wide. So these are known as high frequency counters. So if there's an event that we are counting that occurs at very high frequency and also need to maintain large counts, so the count register is wide, this is a good design to use. Okay, the second topic among arithmetic circuits is parallel counters. Now, simple counter that we discussed in the previous slide has a single count signal or increment signal that comes in, And basically, the counter counts the number of times that that increment signal is asserted. Every time the increment signal is asserted, the count is incremented by 1. By the way, we also have down counters which decrement, and also have up-down counters that increment or decrement according to the value of a control signal. So I didn't discuss those. Okay, so we are only discussing up counters. So here, instead of having one increment signal, we have multiple increment signals. And we basically need to determine the number of these increment signals that are equal to 1, and then present that number down here. So here I have 10 inputs, 10 bits. Say 5 of them are equal to 1, 5 out of the 10. And this circuit computes the number 5 here, which is 0, 1, 0, 1 in binary. Okay, so this is the meaning of parallel counter. A bunch of inputs come in, and we count the number of bits that are equal to 1 among the inputs. And it's called parallel counter as opposed to sequential counter. Sequential counter basically is initialized to 0. And then for each of these signals, it's incremented or not incremented, depending on whether the signal is 0 or 1. So these signals are presented sequentially, and the counter is incremented if the signal is 1 and not incremented if the signal is 0. Here we are providing all the increment signals in parallel, and after a certain delay through the circuit, the count emerges down here. So we don't do sequential but parallel computation. So I won't go through the details of how these counters are designed, but one of the design techniques is basically using full adders, occasionally half adders, to simply add. So 3 bits here are added by the full adder, and we get a 2-bit result. So the count of ones among these 3 numbers is 0, 1, 2, or 3, and the full adder provides this 2-bit number. And the notation 0 and 1 means this is the weight is 2 to the 0, it's in the 0th position. And this is 2 to the 1, it's the carry that goes to the 1st position. So this 0th position bit and this 0th position bit and this 0th position bit are combined to give us a 0th and 1st position bit. This 1 or 1st position bit, this 1st position bit, and this equally weighted bits are combined to give you 1 and 2. And you continue combining bits of equal weight until only one of each is left, and that's basically the number. So for example, here I have 1, 1, bits weighted 2 to the 1, 2 to the 1, and 2 to the 1. Combine them. Here I have a bit weighted 2 to the 2 and another bit. There are only 2 of them, so I use a half adder. And this is my 4-bit result. This is the process in dot notation. Basically, these are the 10 bits initially coming in. After these 3 full adders, each of which combines 3 of those dots into 2 dots. So these are the outputs of the 3 full adders. This is the extra dot that remains unprocessed through that first level. Okay. Then I use a full adder and a full adder to combine these. These are these 2. And these are the outputs of those 2 full adders. Okay. And then at this point, I just need a 3-bit adder, and this is the 3-bit adder that I'm using. It's a ripple carry adder. Okay? So that's basically how one of the ways you design parallel counters. We can also design parallel counters using a recursive method, which basically says if you want to add n bits together, you add half of those bits, or slightly less than half because this is the floor, and the other half, you may be left with an extra bit, Okay, so if n is even, n over 2, excuse me, n over 2 and n over 2 consume all the bits, so you're not left with anything. This bit is 0. If n is odd, then you are left with one bit, and then that bit xn, the nth input, goes here. So you now add the output of this parallel counting network of half the size and the output of this parallel counting network using an adder, and use the carry in of the adder to accommodate that leftover signal if there is any. So here are two examples. Let me just go through this one. A parallel counting network for 15 inputs. Okay, 15 divided by 2 is 7, and with 1 left over. So this part is a 7 input parallel counter. This part is a 7 input parallel counter. And this is the 15th input left over. So each of these boxes is basically an adder. Okay, how do you design a 7 input parallel counter? The two halves will have 3 inputs, and this is the leftover bit provided as carry in, and 3 inputs are basically added using a full adder. A full adder takes 3 inputs and provides a 2-bit output. So these are 2-bit numbers. This is a 2-bit adder, similar to this one. This is a 3-bit sum. When you add two 2-bit numbers with the carry in, you get a 3-bit number. This is a 3-bit number. This is a 3-bit adder with the carry in, which produces a 4-bit result. Okay, so this recursive circuit has an advantage that basically leads to a tree structure, and it is fairly regular in design, so that, for example, you lay out this part of the circuit, and this part of the circuit is identical. You just repeat that layout. Accumulative parallel counters are basically more appropriate generalization of sequential counters, because sequential counters begin with some initial count, and then they're incremented as a result of the increment signal being asserted. Whereas the way we define parallel counter, there is no existing count. You just count the increment signals and come up with a number. Now imagine that you have a qubit initial count, and then these are the increment signals. So you want to add the sum of these increment signals to the existing count. And this can be done by basically doing the parallel counter we just discussed, the recursive design. So this is the count of the increment signal. And then add that to the existing count using an adder. And that's basically the new accumulated count. Of course, the existing count can be wider than, so here I have 15 inputs. So it results in a 4-bit count of the total for the increment signals. But maybe the existing count was a 32-bit number. So you have to add a 4-bit number to a 32-bit number. You need a 4-bit adder, the lower part, and then that generates a carry. And that carry must be accommodated in the rest of the stored count. So you need basically an incrementer or a counter for the upper part here. So you need to increment whenever this carry signal is 1, increment the remaining part of the count, which we know can be done quite quickly from the previous discussion. Okay, this diagram is based on some recent work that I've done in implementing threshold counting networks. So I'll just give you this as an example. So basically, we want to determine whether at least L of the n inputs are equal to 1. So a prime example of this is voting networks. So for example, if I do 2 out of 3 voting, L will be 2, N will be 3. I'm interested in seeing whether at least 2 of the N inputs, of the 3 inputs are equal to 1. Then I can have 5 out of 9 voting, 7 out of 13 voting, and so on. So this is a general strategy for designing such threshold networks. Basically, the recursive design is based on taking one of the inputs and saying, okay, if xn is equal to 0, and I need to have at least L1s among the n inputs, I need to have at least L1s among the remaining n minus 1 inputs. If this input is 0, then if I want L1s at least, I need to have L1s among the remaining inputs. If this input is 1, on the other hand, I only need at least L minus 1 ones among the remaining inputs. So I have basically converted the original problem of at least L out of n to 2 smaller problems with n minus 1 inputs, at least L out of n minus 1, and at least L minus 1 out of n minus 1, and these will be designed recursively in the same way. And this is an example of 5 out of 9 voters. So I want to see whether out of the 9 inputs, x1 through x9, at least 5 of them are equal to 1. So each of these circles is one of these multiplexers. Okay, so x9 is the control signal. It's not drawn here. x9 is the control signal. And therefore, if x9 is equal to 0, I need 5 out of 8 here. If it's 1, I need 4 out of 8 here. And then I continue expanding. So each of these circles is a multiplexer. And at the end, I have these gates at the edges that complete the design. Okay, this is a paper I'm just working on as I record this lecture. It will be made available on my publications page very soon. Okay, so you can refer to that paper for more theory analysis of complexity in terms of circuit complexity and time complexity for these circuits. Okay, the next topic is viewing addition as a prefix computation. And this is an important transition in the theory of computer arithmetic when we realized that addition can be viewed as a prefix computation. It opened up a whole lot of new designs for fast adders, simply borrowing ideas from parallel processing algorithms for doing prefix computation. Okay, so basically a prefix sums computation, as a refresher, we have a bunch of inputs x0 through xn minus 1, and then the prefix sums computation of this sequence is x0, the first number, the sum of the first 2 numbers, the sum of the first 3 numbers, and so on. So each subsequent result adds in 1 number, and all of these partial sums need to be computed as part of this prefix computation. So I start with sum because it's more intuitive. Then I tell you how this is related to carry networks, computation of carries. Okay, so if this operation, so here I talked about addition, but this can be applied to a whole bunch of other operations, such as multiplication, logical and logical OR. Basically, any operation that is associative. Okay, so this is that operation, and this is a circuit that computes that operation. Each new input comes in, so this is the sequential implementation. Each input comes in, it's combined with the previous result. So for example, if the previous result is x0 already computed, x1 comes in, and this computation. And that in the case of addition, this will be an adder. Okay. And then the new sum is computed, and then the next input comes in. So on every cycle, where the cycle length is basically the amount of time the circuit needs to complete its computation, and every cycle a new input is accepted. So this is order n time for n inputs. Now, can we do better? Well, an idea is maybe I can pipeline this adder, make it into a 4-stage pipeline, so that on every clock cycle I can input a new value. So rather than wait for the entire delay of the circuit, I wait only for roughly 1/4 of that delay. Unfortunately, this design will not work because as I add inputs, so let's say this is 0 at the beginning, I add x1, x1 added with 0 then moves to the next stage. The sum moves to the next stage of the pipeline. Then x2 comes in, and x2 is also added to 0 rather than being added to x1. So this doesn't work. This doesn't produce the correct partial sums that we are requiring. The solution is to design this circuit, this particular example. So I have a 4-stage pipelined adder or some other function unit corresponding to the operation that I'm performing. And these are delay elements. And this basically does compute the correct partial sums. I leave it up to you to verify that this does. And the notations that you see here basically are hints as to what is happening in the circuit. So the first input that comes in, so x0 comes in, and the previous result is 0, x0 will emerge here after 12 cycles. It takes a long time. But then x1 comes in, and the sum x0 plus x1 emerges here only 1 clock cycle later. So with this trick and using more hardware, I have reduced the per operand time for this parallel prefix computation by a factor of 4. Well, I can also use 8-stage pipeline, 16-stage pipeline, whatever is possible. But then the design will have to change. And this is the subject of an end of chapter problem. How would this design change if instead of a 4-stage pipeline, I had a 6-stage pipeline or an 8-stage pipeline and so on? Okay, now carry determination is a parallel prefix computation in the following sense. We define for each position of our addition scheme 2 auxiliary signals called the generate signal and the propagate signal. The generate signal is simply the logical AND of the 2 bits. It says that this particular position, because both operand bits are 1s, a carry is generated. A propagate signal requires one of the inputs to have 1 in that position and the other one to have 0. So 1, 0 or 0, 1. And this position would propagate a carry that comes in. It doesn't generate a carry of its own. And of course, there's a third signal that I have not shown here called annihilate. AI is equal to xi or yi. And that basically annihilate, it's xi bar, yi bar. In other words, annihilate signal is 1 if and only if the 2 input bits are equal to 0. Okay, so for each position, I compute these auxiliary signals gi and pi. And then I let carries propagate. This example shown here is a ripple carry network. They can also design faster networks. where these P and G's are combined. So P0, G0, viewed as just one operand, 2 bits, is combined with P1, G1 to provide this carry. Okay, in other words, I have a carry recurrence that says, well, C0 is given to me, okay? So C1 will be equal to 1 if a carry is generated in this position, or a carry comes into this position and it's propagated. So this is basically the carry operator. The carry operator is defined on pairs of PG signals. This can also be viewed as a pair. Simply the G signal for this pair is equal to C0, and the P signal is equal to 0. So there's no propagate over here. So this PG pair is combined with this PG pair, and it gives me a PG pair here, and I'm only interested in the G part, whether a carry is generated for this position. That carry is generated if it's generated in position 0, or it enters position 0 and it's propagated. And similarly for all the other ones, okay? So I'm basically interested in computing the prefixes of this expression that consists of all the pairs P and G, with the operator being the carry operator. Okay, so I can compute the prefix results, partial result, in different ways. So here is one way. This method is due to Brent and Kung, and therefore it's known as the Brent-Kung parallel prefix network. I've shown it with addition. If I replace this with the carry operator and these inputs with PG pairs, then this becomes a carry network. Okay, so Brent and Kung said basically first start by combining pairs of inputs, adding pairs of inputs. X0 plus X1 goes here. X2 plus X3 goes here. Then do a half width prefix computation with what you computed here. X0 plus X1 is one input, X2 plus X3 is one input, and so on. These other lines just go through that box, okay? They're not affected by that box. So this is half size prefix sum network. And then once you are done with that, do these additions to complete the process. Basically, this box computes half of the outputs directly. So this one is X0 plus X1. This one goes through directly. This one is the sum of these two, which is X0 plus X1 plus X2 plus X3, and so on. So those are half of the outputs that we need. The other half will be computed. So X0 plus X1 plus X2 is this missing result. Okay, the recurrences characterizing the delay and cost of this network are shown here. TFN, the time delay, TFN over 2, whatever this box takes, which is half the size in terms of the number of inputs, plus 2. The 2 are basically this level of adders. I'm taking each adder to have unit latency, and this level of adders. And this translates to 2 log 2n minus 1. But we'll see later there's actually 2 log 2n minus 2. If I solve this recurrence, I get this solution. But because of a special feature in the design, it's actually one less than that, which can be justified. Don't worry about this. So it's logarithmic time, roughly 2 log 2n. And the cost, it's cost of n input is cost of n over 2 inputs, cost of this circuit, plus n minus 1. This is how many adders I have. Notice that on every vertical line, there's an adder except this one. So there are n minus 1 adders. And the solution to this recurrence is 2n minus 2 minus log 2n. Again, ignoring these smaller terms, roughly 2n. So this has linear cost, logarithmic delay. And if I expand that design for 16 inputs, this is what I get. This is the top row of adders combining pairs of inputs. This is the bottom row of adders that you saw in the previous diagram. The middle part, after row 1 and before the last row, is basically an 8-input Brent-Kung network. And the reason we have one level less in actuality than what the recurrence suggests is that these two nodes that appear on two different levels in the recursive process can actually do their work in parallel because they're not interdependent. This one receives these two inputs, and this one receives these two inputs. So their inputs are, one does not depend on the other, therefore these two levels are merged into one level of latency. Here's another divide and conquer design. In order to design the prefix network, do a prefix sum of the first half of the input, prefix sum of the second half, and then add the result of this first prefix sum, which is the sum of all the numbers from x0 to xn over 2 minus 1, to each of the partial results from this second prefix sum. This is known as the Ladner-Fisher network. It was actually the first network suggested for parallel prefix computation. Now, theoretically, this is sound. In practice, if you try to implement this as a circuit, this signal having a large fan out can create a problem. So if you're doing 128 inputs, each of these halves will be 64 inputs, and this signal must be fanned out to 64 places, and this creates a problem. Okay. Now, in order to solve this fan-out problem, this is another version of prefix network known as the Kogi-Stone network that doesn't have the fan-out problem. Oh, by the way, I forgot to mention that here the recurrence T of n is T of n over 2 plus 1. These two operate in parallel, so only one delay is included for them, and then just one extra level after that. So this is a factor of almost 2 faster than the previous design, which had 2 log 2n minus 2. But it uses a lot more hardware. The cost recurrence is 2 C of n is 2 C of n over 2, 2 copies of these half-size networks, plus n over 2, the n over 2 adders here, and this will be order n log n. So I cut the delay by a factor of almost 2, but I increased the cost by an order log n factor. Besides this not being practical, and therefore I need to sort of modify the design anyway. So this is basically the Kogi-Stone network that doesn't have a fan-out problem. I leave it up to you to, so instead of one signal being broadcast to all of these upper half results, okay, these get different signals from different nodes there. Therefore, there's no fan-out problem. But the complexity is now more. Whereas I had n over 2 log n, here I have n log n, okay, almost double the cost. The latency is still log 2n, which is the fastest possible. The cost is greater. As I said, this circuit is not practical, so it's not fair to compare the cost of this one to this one directly. Okay, so here I've shown the Brent-Kung network and the Kogi-Stone network side by side for 16 inputs. The Brent-Kung network has 6 levels. Kogi-Stone is faster, it has 4 levels. Brent-Kung is simpler, it uses only 26 cells, whereas the Kogi-Stone network uses 49 cells. It's in fact possible to trade off speed or cost and come up with intermediate designs. And here is one example. So this design basically starts at the Brennkung design. So 16 inputs reduced to 8 inputs. And this last part is basically the adders at the end of the Brennkung design. But instead of doing the 8 input part as another Brennkung design, I'm using a Kogi stone design for the 8 input part. So this is a hybrid network. Part of it is based on the Brentkung strategy and part of it on Kogi stone. And this one happens to have 5 levels, intermediate between those two, and 32 cells, which is intermediate between those two. So these hybrid designs provide trade-offs in terms of latency and cost. Okay, this I'm going to skip this slide in the interest of being able to cover all the things that I wanted to cover. Multiplication, the naive algorithm that we use manually and also in a lot of computer implementation, is an order k squared circuit complexity, order log k time. It's order k squared because in order to multiply two k-bit numbers, the first thing we do, we have to compute these k squared bits. And each of these bits is basically the logical AND of 2 bits. So we already need k squared AND gates, and whatever else we need afterwards is at least order k squared cost. It's order log k complexity because, if we implement it the way we do normal multiplication by hand, the manual pencil and paper algorithm, then it needs, I have to generate this number, then generate this number and add them, then generate this number and add to the result there. It's more than order log k. But we can reduce it to order log k by using tree multipliers. Another way to do multiplication is recursive multiplication. Basically, to multiply two, let's say, 32-bit numbers, I divide each of the numbers into 16-bit halves and then multiply the halves together. Lower part of x times the lower part of a, the upper part of x times the upper part of a. It sits here because of the weight. So this is times 2 to the 16. This is times 2 to the 16. So this will be times 2 to the 32. So it's shifted by 32 bits. And then the upper half of x, the lower half of a, and the lower half of x and the upper half of a are these two numbers. And then I have to add these 4 numbers. And actually, when I try to add them, I realized there are really 3 numbers to add because these two, the top and bottom numbers, do not overlap. So I can put them side by side, making a wider number out of them. And then I have to add this very wide number to these other 2 numbers. And I can use basically carry save addition to reduce this problem of adding 3 numbers to adding 2 numbers. Okay, this too leads to order k squared cost. And more importantly, it leads to order log squared latency. So it's not the best, the fastest multiplier. Okay, Karatsuba, Anatoly Karatsuba, who was a mathematician, basically improved on this recursive algorithm by noting that we can reduce the 4 half multiplications that we had to 3 half multiplications using the scheme while introducing a bunch of additions. Now, additions are much faster than multiplications, so it makes sense to remove one multiplication and add maybe 3 or 4 additions because we gain speed. And his idea is shown here. So this is the original recursive multiplication. A consists of its upper half and lower half, x upper half, lower half. When you multiply out, you get these four terms. So you need four half-width multiplier for these partial results, and then a bunch of additions. Okay? Karatsuba wrote that formula this way, so that you have one multiplication here, AHXH, another multiplication here, ALXL, and a third multiplication, which is AH plus AL times XH plus XL. You can verify easily that this leads to that exact same expression, but it has more additions and subtractions. Okay, so basically when you unroll this recurrence, instead of a factor 4 here, you get a factor 3. Therefore, the rate of growth of complexity, instead of being order k squared, will be order k to the power 1.585. So for very wide multiplications of the type we need, say, in cryptography, this is a worthwhile uh, trade-off, using more adders and fewer multipliers. Okay, if we want to do squaring, our task is a little bit simplified. So I take the same recursive multiplication scheme, apply it to squaring. So the same number appears here. So here I have XL, XL. So this is a squaring operation. XH, XH. This is another squaring operation. And these two numbers are really the same. XL, XH, XH, XL. So instead of generating these two, I just generate one of them and shift it to the left by 1 bit to double it. Okay, so I now have only two things to add, because this one was merged with this one. And therefore, I don't even need carry save addition. I just add these two numbers. Okay, furthermore, the recursive scheme requires two squarers and one multiplier. And squarers tend to be simpler. So instead of three multipliers, even in the Karatsuba scheme, I need fewer than three multipliers. I need two squarers and one multiplier. So squaring, which is a special case of multiplication, leads to simpler circuits. Okay, here I've discussed VLSI issues and bounds. I won't go through all of these. I just show you that for a long time, we knew how to multiply in order log k time and order k log k complexity. Okay, so you immediately see that this is, if this is basically the best we can do, which is it isn't, I'll show you in a minute, then multiplication is a more complex operation than addition, because addition we could do in order log k time and order k complexity. Okay, we had some designs that had order k log k complexity, but we could reduce those to order k. Therefore, addition is a fundamentally simpler operation than multiplication. Now, some progress was made until just recently in 2019. So people sort of suspected that this extra term log k can probably be removed. We can design multiplication algorithm with order k log k circuit complexity. But nobody knew how to do it until in 2019. Harvey and van der Hoeven developed an order n log n multiplication algorithm, which is believed to be the best possible. In other words, we don't even know yet that this is the best possible, but people suspect that we probably cannot do better than order n log n, so multiplication remains more difficult than addition, even with the best possible algorithms. Unfortunately, this best possible asymptotic algorithm is not practical because large constants are hidden in this asymptotic notation, so you can't actually use this to develop circuits. Our circuits will be basically um, order log k time and either order k squared complexity practical circuit or a little bit less than order k squared. For division, I won't discuss actual algorithm, but go through the uh, uh, theoretically based best dividers. Uh, the best known bounds for division are order log k time. Fastest we can divide is in order log k. And the least circuit complexity is order k log k, like multiplication. But we can't, unlike multiplication, we can't achieve these two simultaneously. In other words, we can't design a divider that has order log k latency and order k log k complexity. Okay, going to the previous slide, this is basically the best we can do. If we want to have order log k latency for a divider, we have to pay a very high cost, order k to the power 4. Okay, if we want to, uh, if we are willing to achieve a little bit higher latency, then we can reduce the cost to order k squared. Okay, so going back to this slide, this is basically the result I referred to. In 1984, it was discovered that you can do division in order log k time with hardware complexity order k to the 4th. So basically, based on these results, division must be viewed as a fundamentally more difficult operation than multiplication based on our current knowledge. Someday maybe somebody discovers a division algorithm that is asymptotically as efficient as multiplication, but we don't know such an algorithm yet. Okay, so let me end my discussion of arithmetic uh, circuit model for arithmetic operations and go to Fourier transform, or more precisely, discrete Fourier transform circuit. Okay, a Fourier transform circuit receives n inputs, and these inputs can be basically real numbers or complex numbers. Either way, it works. So there are n inputs, a vector of n inputs. We apply the discrete Fourier transform operation on it, and we get another set of n inputs. This is the transformed version. So it converts a vector of inputs into a vector of outputs. For reasons that will become clear shortly, this is known the time domain signal or input. This is the frequency domain signal or output. And then inverse DFT converts these numbers back to the original input. So we have DFT and inverse DFT. So we are motivated in this transformation because some operations are easier to perform on this transformed version. So we pay the overhead of DFT to obtain these, and then maybe later we want to make some changes in this, and then transform back to the original time domain inputs. This is known as endpoint DFT because there are n inputs. There are other important transforms that are considered in signal processing. I just named them here to show you that DFT is just one of many transforms that exist. It's perhaps the most useful. But these other ones, such as Z transform, which is a generalized Fourier transform, discrete cosine transform, which is used in JPEG image compression, and Haar transform, which is a wavelet transform. And like DFTs have this fast version. The fast version of this is called the fast Fourier transform, FFT. In fact, we hear FFT more often than DFT, the fast version, because once we know that fast version, there's no reason to use any other version. But DFT is the computation that is defined, and FFT is an algorithm for implementing that computation. Okay, so DFT is defined as follows. These are the inputs, the x's, these are the outputs. Each output is a weighted sum of all the inputs. So each of the inputs is multiplied by a weight, and that weight is some power I times j of omega n, which is a constant. Okay, I'll show you what that constant is. So there's some constant that is raised to some power I times j, and that resulting value is multiplied by xj. So xj is weighted by this value, and the weighted sum of the xj's gives you yi. So each yi, computation of each output, requires n multiplications and n additions to sum these values. So order n computation time for each output, therefore order n squared time for the naive algorithm that basically does multiplies and adds. So what is omega n? Omega n is the nth primitive root of unity. What does that mean? It's a root of unity, the nth root of unity, because omega n to the power n, remember omega n is a constant, this is just a notation. If you raise that to power n, you get 1. So it's basically omega n is an nth root of 1. But there's a condition that other smaller powers of omega n should not equal to 1. So we are looking for a number omega n such that when raised to the power n, it yields 1. But raised to any smaller power, it doesn't yield 1. Because otherwise, 1 is also an nth root of 1, but it doesn't satisfy. It satisfies this part, 1 to the power n is 1. But 1 to any smaller power is also equal to 1. So omega 4 is I. Okay? Because I to the power 4, I squared is minus 1, and I to the power 4 is 1. So it satisfies this first requirement. And it satisfies the second one because I to the power 1 is I, is not equal to 1. I to the power 2 is minus 1, again not equal to 1. I to the power 3 is negative I, again not equal to 1. So omega 4 is equal to I. Similarly, omega 3 is this complex number. Omega 8 is this complex number. And here's the interpretation of omega 3 in graphic terms. So this is omega 3 to the 0, or omega 3 to the power 3 equal to 1. Omega 3 to the power 1 is minus 1 plus j square root of this complex number. And this is omega 3 to the power 2. Okay. So this is the discrete Fourier transform of a cosine waveform. Okay, so the input was a cosine waveform, or the basically digitized version of that. And the output of the Fourier transform is this. Basically, frequency of the cosine waveform is 1/10 of the sampling frequency. Or we can say that the sampling frequency is 10 times of the frequency of the input waveform. And then this reveals, large components at the 1.1 frequency and 0.9 frequency, and smaller ones at other places. This is more of the same with different number of inputs from 64 to 256. So now I can reformulate the discrete Fourier transform operation as a matrix by vector multiplication. So the output vector y is the product of this matrix. So these coefficients here are put into a matrix form times x. And this matrix has a special structure. Okay, the first row is all ones. The next row is 1, omega, omega squared, omega cubed, and so on. Remember that omega, all these powers of omega less than n are not equal to 1. So these are different numbers. Omega squared, omega 4, omega 6. So if this were a general matrix by vector multiplication, I would need order n squared operation, because I have to multiply a row of this matrix by this column vector x using order n operations to find one element of y. So a general matrix by vector multiplication has order n squared complexity, whereas this being a special matrix, not an arbitrary matrix, might allow us, and in fact it does in the fast Fourier transform, to do this matrix by vector multiplication faster. I'll show you how in just a minute. If you are interested, if you have not been exposed previously to discrete Fourier transform, here are some resources that you can use. These are basically all YouTube videos. The first one is General Introduction to Fourier Series in 16 minutes. I recommend that you pursue at least one of these. An Introduction to Fourier Transform, an 11-minute video is the second source, and a Visual Introduction to Fourier Transform, a 21-minute video. So at least do one of the first two, which are shorter, to, if you're not already familiar with Fourier transform, to get a feel for what it is and why it is used. So a few applications of DFT. Here is a signal superimposed with noise. So these spikes are basically noise that have been introduced to the signal because of a noisy transmission channel, for example. If you find the discrete Fourier transform of this noisy signal, and then basically eliminate the high frequency components from the transform version, basically zero out those terms corresponding to high frequencies, and then put the new values through an inverse DFT, you recover the original pure signal, non-noisy signal. So DFT here is used as a tool for noise removal by doing the transformation from the time domain into frequency domain. In the frequency domain, remove the terms corresponding to high frequency, and then do inverse DFT. Of course, there are also low-pass filters that directly, hardware implemented low-pass filter. But this is a more general approach because this DFT is useful for many types of low-pass filters, not just a particular one that you can design in hardware. Okay, here's another signal corrupted by random noise. We are interested to see what the original signal was. We put it through DFT, and basically the DFT shows us that the original signal had these two frequencies, 50 and 120. And everything else was noise that was added to it. The uncorrupted signal, in fact, was this 0.7 sine of 2 pi 50t. plus sine of 2 pi 122t. So it was two sinusoidal uh, functions with different weights, 0.7 and 1. That was corrupted by noise, so you don't see in this noisy signal the original frequencies, but the Fourier transform exposes those two frequencies for us. A third example, this is touch-tone dialing. Now, of course, it's ancient. We don't use it anymore. In touch-tone dialing, there's a keyboard. In this case, not just the numbers, it's a hex keyboard. And then whenever you press a key, the sound is generated that is a combination of two frequencies. So when you press 1, it does this its distinctive tone composed of two sounds, 697 hertz frequency and 1209 hertz, and so on. So when you press one button, the received tone at the other end can be put through a discrete Fourier transform, which exposes the two frequencies. Okay, so this frequency and this frequency appear in that input. Of course, there will be noise in general. The noise does not affect this deduction when we find the two frequencies. And once you know the two frequencies, you know which button was pressed. Okay, so what is fast Fourier transform? Fast Fourier transform was discovered in the 1960s by Cooley and Tuckey, so it's sometimes called the Cooley-Tuckey algorithm, who observed that in order to do an endpoint Fourier transform, you can do a Fourier transform on even index inputs, x0, x2, x4, x6, so that's half the size, and a Fourier transform on x1, x3, x5, and x7. So the first Fourier transform, call it U, the second one V. So U is Fourier transform of the even index input. So it's a recursive structure, okay? If you have 8 inputs, you do 4 input Fourier transform, computing the U's and the V's. Now for 4 input Fourier transforms, you do 2 input Fourier transforms and so on. You apply this recursively. And then yi, the ith input in the original Fourier transform, is ui plus some weight times vi. So once you have these two half Fourier transforms, you can compute the original outputs. And then here's some alignment problem. This equality should have appeared here. And this one is ui minus. So this weight is multiplied by v, and the result added to ui. This weight is multiplied by vi, and the result is subtracted from ui. So this value is computed, it's added to ui, and it's subtracted from ui to get these two outputs. This is known as a butterfly operation. Okay, we'll see why it's called a butterfly operation. So for now, accepting that this works, the running time of this algorithm is 2t of n over 2 for sequential implementation, because you have to do this half Fourier transform and this half Fourier transform. And then you need n multiply add operations, okay, n of these. And the result is n log n. Remember that the naive algorithm was order n squared. This one is order n log n. If you do these two half transforms in parallel, two separate half circuits, then the recurrence will be t of n is t of n over 2 plus 1. And if you do all these additions in parallel, and this will be order log n, which is a pretty good running time, logarithmic running time, whereas the naive sequential algorithm was order n squared. Okay, so this FFT is actually a special case of this more general scheme. So if you have a one-dimensional DFT, you can put the elements into a matrix. So this shows the order of the elements. The first three elements go here, the next three here, and so on. Then you do DFT on the columns, multiply the numbers by some constants known as twiddle factors, and then transpose this matrix, and then do DFTs on the columns, and that gives you the overall DFT. Now, if this has two columns, so basically, let's call these x0, x1, x2, x3. This has only two columns. You have x0, x1, x2, x3, x4, x5. So these are the even index inputs. These are the odd index inputs. So you do DFTs on those two. And then when you transpose this, there will be two rows. So you do 2-point DFTs. And these are essentially 2-point DFTs. Okay, so a 2-point DFT is 1-point DFT and 1-point DFT. So it's basically a multiply add. Okay, so this is a more general factoring based algorithm. In the case of FFT, the 2D structure here is n over 2 rows by 2 columns. Okay, so this is the basically hardware implementation of FFT algorithm. Remember, I said take the inputs, divide them into even index. So these are the even index. Now why they appear in this particular order will become clear shortly. So x0, x2, x4, x6, do an FFT. Take the odd index, do FFT. So those are the U and V vectors. And then do 2-point DFT between U0 and V0 to find Y0 and Y4, between U1 and V1 to find Y1 and Y5, and so on. And then what is a 4-point DFT? Well, so let's renumber these as X0, X1, X2, X3. So these are now X0 and X2. These are the even indexed entries in this half. And these are the odd index entries. So 2-point DFT, 2-point DFT, and then merge the results into this. Okay, so the butterfly network, which we saw before as an interconnection network when we're discussing shared memory, actually arose from this mapping of the DFT computation to hardware. And this is basically the same diagram drawn with some more details shown. In fact, those weights that are used. So when this input is combined with this input, this one is given this weight. And when this is combined with this one is given this weight. So the weights are explicitly shown. So this is a butterfly processor. The second input is multiplied by a twiddle factor. That's that weight that we were talking about. And if we want to use this butterfly network for general computation, this is not a constant, but it's something that we read out from memory. So all the possible constants that are involved are stored in a memory unit, and then we fetch the particular constant that is applicable to this operation, do this multiplication, and then add and subtract to find the two outputs. So a butterfly processor has a multiplier, an adder, a subtractor, and possibly a memory if we want to make it more general, so that any weight can be applied here, not just one specific weight. Because remember, when we go to this, if these are actually different butterfly processors, each of them uses a specific weight. So this one uses this weight, this one uses this weight. So if these are separate hardware elements, you just need that one thing that can be wired in. But if I want to reuse a processor to do this, and then later perhaps do this with a different weight, then I may want to provide a memory unit to hold those different, the set of weights that I need. So this is a 16-point DFT shown in full. So we have 2-point DFTs, then 4-point DFTs, then 8-point, and the 16-point. And these numbers here are basically powers of that omega n that are involved. So rather than writing the constant, I just write the power. So the butterfly processor takes A and B, and the J shown on this line is basically the power of omega that is used in this addition and subtraction. So this is again a fully specified 16-point FFT network. And furthermore, in the previous designs, I wrote the inputs, in this weird order. That order is actually called the bit reversal order. So if you write these as 3-bit binary numbers, the 0 is 0, 0, 0. 4 is 1, 0, 0, whose reverse is 0, 0, 1. 2 is 0, 1, 0, whose reverse is also 0, 1, 0. And 6 is 1, 1, 0, whose reverse is 0, 1, 1. So you basically have 0, 1, 2, 3 if you take these indices in reverse order. So in this diagram, that bit reversal permutation is shown as wiring. So the inputs appear in order from 0 to 15, and outputs appear in order from 0 to 15. And that rearrangement, so that we put all the even index elements on top and all the odd index element at the bottom, is explicitly shown in this diagram. Okay, I'm gonna skip this and just go directly to, now if you're doing a 1024 FFT, this circuit for 8 input has 3 columns. Remember that this leftmost column is not really any hardware. These are just inputs coming in. But beginning with this column, you have the butterfly processors. So you have 3 columns of butterfly processors, or more generally log 2n. So if these are 1024 points, you will have 10 columns of butterfly processors. So 1000 times 10, 10,000 circuit elements. If you want to save on hardware, you map this hardware in this direction into a set of only n processors. Because what happens here is that these processors do their job and then pass on their values to these processors. And after they pass on their values, they remain idle. They have nothing else to do. And similarly, this column is idle at the beginning, and when it receives values from this column, it does its processing. So at any given time, only one column is active. Therefore, it makes sense to try to share the hardware for these columns by providing only n processors, and then those n processors do the job of these n, and then later the job of these n, and finally the job of. However, the connectivity pattern in this drawing of the butterfly network is different. So it's kind of hard to try to implement those different connectivities. So the inputs come in, these outputs are generated, but those outputs must be fed back differently between these two columns compared with between these two columns. So what's the solution? It turns out that I can redraw the butterfly network so that the connectivity pattern between adjacent columns is identical. This is easily verified. I've just removed things, okay? So x0 is here, it's still here in the new drawing. x4 was here, I've put it down here in the original order, basically. And now the connectivity pattern is exactly the same between all the columns. Okay, notice that now the output appears in this weird order, y0, y4, y2, y6, but that's not a big problem. You can just rearrange the outputs using a permutation network. Now, once I've done this uniform design of the butterfly network, now the mapping becomes simple. So now what I've also done is I've done some additional simplification. Notice that here x0 is connected to these two cells. x1 is connected to these two. Instead of connecting to both of those, I connected to just one of them and let these two exchange values so that this one becomes aware of that value x1. So x0 is connected here, x1 is connected here, x2 is connected here, and so on. And connections are also established between these. Okay, so that's basically this new version with even fewer connections. Then, once this column has done its job, the first output is routed to the first input. This is this path. The second output is routed to the third one. So this one goes here to the third one, and so on. Okay, so this uniform connectivity between columns allows me to reuse one set of n processors to do the job of these log n columns, therefore saving time while the latency is not increased. It's increased a little bit because of the need to store values in these registers, so that setting those registers takes some time. Okay, but it's still the latency is order log n, although each of these cycles a little bit time is added because of the need for storing values. Okay, so this is basically mapping of the butterfly network in this direction, getting n processors instead of n log n processors. An even more economical implementation is when you map the processors in the vertical direction, so that you have one processor doing the job of this column, one doing the job of this column, and one doing the job of this column. So in this example, you have only 3 processors. In the case of 1024 inputs, where you have 10 columns here, you would have only 10 processors. Of course, that's much less parallel, but it's a lot more economical. Now this becomes a little bit tricky in terms of timing, because this processor does the job of this one and this one, operating on x0 and x4, and then when it wants to do the job of this one, it does on x1 and x5. So that timing requirement is honored by these shift registers. I won't have time to justify this. I'll just show you that there are 4 registers in this loop, 2 in this one, 1 in this one. So the pattern is, if n is a power of 2, this is n over 2, n over 4, n over 8. And this leads to the alignment of values correctly for them to be added. Now these diagrams have a slight error in that this multiplication is shown after the subtraction. It should come on this side, because first you have to multiply this input by its associated weight and then do an addition and subtraction. I apologize for that. So this should precede the subtraction rather than follow it. But other than that, the design is correct. So again, the same error appears here. This must come on this side. The multiplication should come over here. So this is basically the timing. So x0, x1, x2 come in sequentially. As x0 comes in, it has to be combined with x4. So it is kept in these registers for 4 time units until x4 arrives. And now I have x0 here and x4 here, and this one can do its job. Similarly, x1 should be kept for 4 time units. So x0 is put in here, x1 is put in here into this shift register, and then eventually x0 emerges here at the same time as x4 is coming in, x1 comes here at the same time as x5 is coming in, and the rest of it you can follow through. So this is the timing requirement in order to align the things that are combined together, x0 and x4, x1 and x5, and then here this value and this value and so on. And then the 8 outputs emerge from here after a certain initial latency of 8 time units. Okay, so basically the message here is that the original butterfly network requires order n log n complexity, which can be quite high if n is a large number. So you can do this more economical order n implementation with a little bit more time. So the time penalty here is very small. Or you can do this order log n hardware implementation, which a lot more, uh, a lot more latency, but much less hardware. Okay, let me stop at this point. I hope you stay safe until the next time when we'll talk about mesh connected processors. We move into part 3 of the textbook. Until then, stay safe. Goodbye.